Hello everyone and welcome to the presentation of our paper Interactive Focus and Context Rendering for Hexahedral Mesh Inspection. Hexahedral meshes have widespread use in numerical simulation methods using finite elements and finite volumes. It is one of the grand challenges in hex meshing to construct meshes with as low as possible deformations. Hexahedral meshes consist of so-called hexahedral elements, which in turn consist of 8 corner vertices, 12 edges, and 6 faces. The Jacobian deformation ratio can be used to measure the deviation of an element from the perfectly shaped element. On the top, you can find examples for hexahedral elements. On the left, we have the perfectly shaped element with a Jacobian deformation ratio of 1. And on the right, we have a slightly deformed element. On the bottom, you can see different examples for simple hexahedral meshes. In this image, you can see a visualization of a mechanical model visualized using the state-of-the-art hex mesh visualization program Hexalab by Baracci et al. Hexalab visualizes the boundary surface of the hex mesh. Face colors indicate the deformation of the respective cells. This type of visualization has the problem that the interior of the object is occluded by the opaque boundary surface. The authors of Hexalab tried to solve this problem by equipping the user with slicing, peeling, and cell quality filtering operations. These operations remove certain cells from the visualization. As a proxy for this filtered data, a transparent boundary surface is drawn on top of the object, and so-called singular edges are shown sparsely in empty regions to provide a context view. However, this approach has two disadvantages. When exploring a new dataset, the user needs to actively search for interesting regions by using slicing, peeling, and cell quality filtering operations. Most of the time, there is not one single view from which all interesting features of the dataset are visible due to occlusion. Also, when putting focus on some part of the mesh with the help of filtering operations, we lose almost all information about the context except for singular edges. In this image, you can see the contextual volume rendering of our focus and context rendering technique. Coarse mesh edges are blended into a volumetric representation of the mesh. Cell deformations are mapped to color and opacity. Here, blue means low deformation, orange means medium deformation, and red means high deformation. Furthermore, users can explore the hex mesh by moving a lens-like hotspot. In this lens region, more detailed edge structures or the boundary surface of highly deformed cells can be shown. For our technique, we utilize a level of detailed edge structure based on the merging of so-called hexahedral sheets. A hexahedral sheet is a set of cells sharing parallel edges. Using this LOD structure, the user can control the number of edges shown, both in the context and the focus region. Our rendering technique consists of two major components: the contextual volume rendering on the one hand, and focus and context cell edges selected from a user-specified LOD level on the other hand. The transparent geometry is rendered by using the order-independent transparency algorithm per pixel linked lists by Wang et al. The user can put focus on a mesh region by using a screen space or object space lens. Both the volume and the edge rendering are done in one single rendering pass. We compute the distance of a fragment to the closest face edge and consider the fragment to belong to an edge if it is close to an edge and not discarded due to the use of the LOD structure. Here you can see an image of a bunny hex mesh, rendered using normal direct volume rendering. The cell deformations are mapped to color and opacity. This way, the user can see potentially interesting regions at once. However, the cell structure is hard to see due to depth attenuation. This creates a blurry look. When simply rendering transparent cell faces without depth attenuation, the cell structure becomes more visible due to overlapping faces. Also, this approach is computationally faster, as we do not need to track view ray entrance and exit points for computing the optical depth for depth attenuation. If we assign a higher opacity to fragments close to face edges, the cell structure is emphasized even more clearly. Additionally, using our single-pass rendering approach, context edges from a sparse LOD level can easily be added into the volume. In the focus region, the edges are rendered with a white outline to make them stand out. The user can also choose to select a lower LOD level for the focus edges. Using a screen space lens, a smooth transition from the focus region into the context can be achieved. The different parts we saw earlier can then be added into one single visualization. We can also add the edges or faces of the most strongly deformed cells in the focus region. Here we see a relatively simple dataset of a carved cube. On the left, our contextual volume representation can be seen. On the right, classical visualizations of the same mesh are shown. When viewing the boundary surface without any filtering operations, the interior of the object is not visible in this case. As we remove different cells, we can get more insight into the structure of the object. However, there exists no single view where all important features of the dataset are visible. This can be fixed by using our contextual volume representation on the left. Here you can see a comparison of our technique to a visualization created using Hexalab by Bertsch et al. In the middle, and a visualization using the topological visualization method by Xu et al. On the right. The visualization on the right focuses solely on the topology of the hex mesh and ignores geometric cell deformations. In this last part, we will show you the approach presented in action. Here, the hex mesh we saw earlier is analyzed using a screen space lens. For the next hex mesh, we will first show you a contextual volume representation of the mesh. A camera flight is used to give an overview. In this region on the bottom right, we can see a deformed cell on the inside of the mesh, indicated by the red color. A screen space lens can be used to inspect the mesh in more detail. Apart from a screen space lens, object space lenses can also be used for inspecting the object. Thanks a lot for your attention. Please feel free to ask anything you have in mind regarding the content of the paper.